Imagine trying to track the exact speed, like the precise lane position and the final destination of every single car across an entire country, simultaneously in real time.
Yeah, that would just completely break a normal computer.
Right, exactly. A classical computer wouldn't just lag, it would literally hit a physical wall. And, well, that is exactly the problem we are looking at today. Except instead of cars, we are talking about tracking particles to, literally bottle a star.
Which is just a crazy concept to begin with.
It really is. So whether you are prepping for a highly technical meeting or trying to catch up on computational physics, or you are just insanely curious about the future of energy, you are in the exact right place.
Yeah, we are looking at a really fresh piece of research today. It's from August 2025 by researchers at Classiq Technologies. Right. The paper is titled Implementation of a Quantum Linear Solver for the Vlasov-Ampere Equation. And it sits right at that bleeding edge where quantum computing just crashes into nuclear fusion.
Okay, let's unpack this, because our mission for you today is to extract the ultimate aha moments from this highly technical paper.
And there's some really good ones in there.
Yeah, we want to understand how new quantum software tools are, unlocking the math needed to simulate fusion. And we are going to do it without making you feel overwhelmed by the dense equations.
Hopefully.
Yeah, hopefully. So let's start with that physical wall classical computers are hitting. I mean, why do we even need quantum computers to build a fusion reactor?
Well, to understand the bottleneck, we really have to look at the physics of a fusion reactor, like a tokamak or a stellarator.
The big donut-shaped machines.
Exactly, the donuts. You're trying to contain this electrically charged gas, a plasma, that is literally hotter than the center of the sun.
Wow.
Yeah, and because it's so chaotic, you absolutely cannot let it touch the walls of the reactor. If it does, the fusion reaction just instantly dies.
Right, so you have to keep it perfectly suspended using, like, giant magnetic fields.
Exactly. And engineers have to simulate this behavior using what are called kinetic collisionless plasma models.
So they need a math model that can predict exactly what this chaotic, superheated gas is going to do before they even turn the physical magnets on.
Right. And that requires coupling two massive mathematical frameworks together. You've got Maxwell's equations on one hand.
Which describe the electric and magnetic fields, right?
Exactly. And then you have the Vlasov equation, which describes the actual motion of the particles within those fields.
Okay, so fields and particles interacting.
Yeah, and the core variable linking all this together is the distribution function. The paper writes it as f of x vt.
Okay, which brings us back to the traffic analogy from the start. That function isn't just, looking at the density of cars on a highway.
No, not at all.
It tracks the probability density of finding a single particle at a very specific position, x, with a specific velocity, v at a specific time, t.
What's fascinating here is how classical computers try to handle that massive data requirement.
Wait, how do they even do that?
Well, they rely on discretizing this phase space over a fine grid. They try to chop the continuous volume of the reactor and the continuous spectrum of velocities into tiny, manageable squares.
Sort of like pixels on a screen.
Yeah, exactly like pixels.
Yeah.
But to get the resolution you need to accurately predict a chaotic plasma, that grid has to be incredibly fine.
I can imagine.
So you end up creating matrices of data that are so massive, classical solvers literally just run out of RAM. The memory demands become a physical roadblock to fusion energy.
So you simply can't plug enough memory chips into a classical motherboard to hold the entire 3D state of a fusion reactor at once.
You really can't.
So the researchers at Classiq turned to the quantum realm, but they didn't just plug the whole 3D donut tokamak problem into a quantum computer for this paper, did they?
No. They stripped the problem down to a 1D model to test their algorithm.
Okay, so a one-dimensional straight line, basically.
Right. They focused on a simplified 1D electron plasma, and to simulate the conditions of a reactor, they drove this 1D plasma with a monochromatic external radio frequency drive.
Monochromatic external RF drive. Let me make sure we understand the terminology there.
Sure.
That basically just means they are mathematically pumping a single pure radio frequency into this 1D line of plasma, right? Which I guess mirrors the physical RF heaters they use to pump energy into actual fusion devices?
Yes, exactly. It simulates that external energy input. But the real cleverness of this paper is how they handle the resulting chaos.
How so?
They use a technique to linearize the problem. Instead of trying to simulate the massive nonlinear turbulence of the whole plasma all at once, They just isolate a tiny perturbation.
A tiny perturbation like a ripple.
Right, a small ripple they call G. And they measure how it deviates from a background Maxwellian distribution, which they call capital F.
Meaning the plasma is assumed to be sitting in a natural, balanced, stable state. That's the Maxwellian distribution.
Exactly.
Then we hit it with a radio wave, and instead of tracking the whole ocean of plasma, we just measure the tiny ripples on the surface.
That is a perfect way to picture it. And by making that assumption, they achieve something crucial mathematically. They transform incredibly complex partial differential equations, or PDEs, into an ordinary differential equation system.
And an ODE is much easier to solve.
Way easier. This ODE system only has two variables to track: the perturbation G at a given position and velocity, and the resulting electric field E.
So they condense this into a massive linear equation.
Right, written as I omega 0 plus A times CSI equals B.
I mean, I am looking at this simplification, and I have to push back a little here.
Go for it.
If we simplify the math down to just a one-dimensional straight line, and we are only looking at the tiny ripples instead of the full chaotic ocean, aren't we kind of losing the real-world application? A 1D straight line doesn't really help me build a 3D magnetic cage.
It's a fair point. And the authors actually explicitly acknowledge that limitation.
Right.
But, science builds in steps.
Right. You got to walk before you can run.
Exactly. By casting this intensely complex plasma physics problem into a linear format, they make it perfectly suited for a specific tool, a quantum linear system solver.
Okay, so it's a test case.
Right. The goal of this August 2025 paper isn't to solve the fusion energy crisis today. The goal is to prove that the quantum technique works under the hood. They are basically building the mathematical scaffolding.
Yeah, if you can't run a 1D ripple on a quantum machine, you have absolutely zero hope of running the 3D storm.
That is exactly it.
Okay, so we have to prove the tools work before we build the house. So we have this linear matrix, this mathematical grid representing our 1D plasma ripples. How do we actually force a quantum computer to solve it?
Well, the chosen quantum routine they deploy is called Quantum Singular Value Transformation, or QSVT.
QSVT.
Got it. And QSVT is highly regarded in the field because its complexity scales polylogarithmically in dimensions.
Let's break down polylogarithmically for a second. That is a mouthful.
It is.
It essentially means the algorithm is incredibly resource efficient as the problem gets bigger, right? Like, if the matrix doubles in size, the time or resources the quantum computer needs to solve it only grows by a tiny, manageable fraction.
Rather than blowing up exponentially, yeah. It is the kind of scaling classical computers can literally only dream of for these phase-based problems.
But there's a catch, isn't there?
Always. To use QSVT, you face a major hurdle. You can't just hand the quantum computer your classical matrix of plasma data.
Why not?
You have to perform a process called block encoding. You basically have to take your target classical matrix, B, and embed it into a much larger quantum unitary matrix, U.
Okay, here's where it gets really interesting. Let me try to reason through this.
Go ahead.
A unitary matrix in quantum mechanics means the operation has to be perfectly reversible. That's like a foundational rule of how qubits behave, right?
Correct. Total reversibility.
But our classical physics matrix for the plasma isn't reversible. It's just a rigid block of data, like a snapshot of the mass. So I'm struggling to see how you force rigid, one-way classical data into a reversible quantum format without just, breaking the data entirely. It's like fitting a square peg into a round hole.
It is very much like that. Think of the classical matrix as a one-way set of written instructions. To make those instructions unitary, you have to translate them into a complex set of interlocking revolving gears.
Okay, gears. I can picture that.
In this gear system, turning any single gear backward perfectly undoes the entire physical action. Block encoding is the act of building this massive gear system, embedding your one-way instructions inside a specific square slot within those round gears, and ensuring the rest of the machine just spins in a way that allows the whole thing to run backward.
Wow. So you're building an enormous quantum machine around your data just to satisfy the laws of physics.
Pretty much.
And the rest of those gears, the parts not actively holding your data, are just what the paper refers to as mathematical garbage.
Yeah, you are basically padding the matrix with extra information to maintain that reversibility.
How much padding are we talking about?
Well, to map the phase space of the plasma into this gear system, the paper uses a grid of 2 to the power of nex times 2 to the power of NV points.
Okay.
To represent that actual data, they need NX plus NV plus 1 logical qubits. But to build that surrounding gear system, that unitary matrix, They have to use 8 extra qubits just for the block variable.
They are throwing 8 extra qubits at the problem purely to manage the translation between classical math and quantum physics.
Exactly.
But wait, how do you actually map the intricate physics of plasma into quantum logic gates?
It requires an algorithmic technique called linear combination of unitaries, or LCU.
LCU?
Yeah. Think about the Vlasov equation we broke down earlier. It describes the bulk motion of the plasma in the center, but it also has strict boundary conditions for what happens at the edges of our 1D line.
Right, the plasma can't just go on forever.
Exactly. So LCU allows the researchers to build separate quantum gear systems for the bulk derivative terms and the boundary conditions.
Oh, and then they stitch them together.
Yes, they carefully stitch them together, they combine them linearly inside that giant unitary matrix.
Building that gear system gate by gate, ensuring the boundaries of the plasma behave correctly while keeping the entire matrix mathematically reversible. I mean, coding that by hand sounds agonizing.
It is a nightmare.
It just sounds like a fast track to introducing a million human errors into the circuit.
And that brings us to the most significant breakthrough of the paper, actually. Typically, when researchers build these quantum models, they rely on rigid, low-level quantum coding.
Like what?
Well, the baseline standard is often Qiskit. It is highly granular. You are manually telling the individual qubits what to do, drawing lines between them gate by gate.
So very manual.
Very manual. But the Classiq researchers abandoned that low-level approach. They use a high-level quantum programming language called QMOD.
QMOD. And the paper explicitly shows a 2-order of magnitude reduction in CX gates, right? That's roughly 100 times fewer quantum operations when using QMOD compared to the Qiskit baseline.
Yes, it is a massive reduction.
But how? How does a software compiler actively compress a physical quantum circuit to that degree?
The compression comes from how QMOD automates multi-control and adder implementations.
Okay, break that down for me.
Sure. In a quantum circuit, you frequently need an operation to trigger only if several other conditions are met. Say you want a target qubit to flip, but only if 5 specific control qubits are all in one state.
Like an if-then statement in normal coding.
Exactly. But in low-level quantum coding, you can't just draw a single line connecting them all. You have to build a massive cascading pyramid of intermediate 2-qubit CX gates to check each condition sequentially.
Wow. So a single logical instruction, like flip this if these 5 are active, balloons into dozens of physical gate operations.
Precisely.
And because current quantum hardware is noisy, I imagine every single one of those CX gates introduces a tiny chance that the qubit decoheres and the whole calculation just collapses into static.
That is exactly the problem. Every gate is a risk. QMOD solves this by looking at the global math of the Vlasov equation.
So it looks at the big picture.
Right. Instead of rigidly building those gate pyramids, the compiler automatically finds mathematical shortcuts. It determines the most efficient way to route those controls and adders algebraically, bypassing the massive cascades of CX gates entirely.
That is incredibly smart.
Depending on whether they ask the software to optimize for the width of the program or for the raw CX counts, QMOD instantly restructured the circuit to use 100 times fewer physical operations.
It's basically the difference between a programmer trying to build a modern 3D video game by manually typing out millions of ones and zeros to make a digital apple fall to the floor.
That sounds painful.
Versus using a physics engine, right?
Yeah.
Where you just apply an overarching rule of gravity and it handles all the underlying math for you.
That's a great way to put it. And if we connect this to the bigger picture, a 100x reduction in gates fundamentally shifts the timeline of quantum computing.
Because we can do more with less.
Exactly. We don't have perfect, fault-tolerant quantum computers yet. We have noisy, fragile qubits. If you reduce the number of operations by a factor of 100, a simulation that was physically impossible to run on today's hardware suddenly becomes viable.
So the software abstraction is leapfrogging the hardware constraints. It's allowing physicists to run deeper simulations much sooner than anticipated.
That's exactly right.
The code got smarter, so the physical machine doesn't have to work as hard. I mean, it is a brilliant paradigm shift. But, you know, as we do with all cutting-edge science on this deep dive, we have to look at the limitations.
Yeah, we have to be realistic.
There is a catch in this paper. Despite reducing the quantum gates by a factor of 100, the authors explicitly state they do not expect any quantum advantage for this specific one-dimensional problem.
That is true.
I have to ask why. If the algorithm is this heavily optimized, why would a classical computer still beat the quantum machine here?
The limitation lies in a mathematical property called the condition number.
Condition number, okay.
In linear algebra, The condition number basically measures how sensitive a function is to tiny errors or changes in the input.
Right.
For this specific linearized Vlasov-Ampere equation, as you increase the grid size to discretize the differential equation.
As you chop the phase space finer to get a clearer picture of the plasma.
Exactly. As you do that, the condition number grows rapidly.
So as we try to get a better resolution of the ripples, the math itself becomes highly unstable and sensitive to error.
Yes. And the efficiency of a quantum linear solver, even one using QSVT, is heavily dependent on that condition number remaining low.
Oh, I see.
Because it scales so aggressively in this 1D model, the quantum computer is forced to run exponentially more samples just to overcome the sensitivity and produce an accurate result.
And that sampling penalty completely eats up the polylogarithmic speedup we were so excited about earlier.
It does. Classical methods, while memory-heavy, don't suffer from this specific quantum sampling penalty in 1D, so they remain faster for now.
So, what does this all mean? If the authors freely admit there is no immediate quantum advantage here, and my desktop computer might theoretically crunch this 1D math faster, why should you, the listener, care about this paper? Why is this a breakthrough worth our time?
This raises an important question about how we view scientific progress. Knowledge is most valuable when applied incrementally.
Right, the stepping stones.
Yes. The breakthrough isn't the 1D solution. It is the methodology the software unlocked. The paper proves that encoding incredibly complex classical plasma physics into reversible quantum functions can be done with extreme resource efficiency.
Okay.
And there is a vital detail in the results regarding the scaling factor, which they denote as S.
The scaling factor. Wait, does this relate to the mathematical garbage we talked about earlier, like the extra gears surrounding the data?
It does, yeah. They note that their implementation does not add overhead from the data embedding itself.
Oh.
The scaling factor, S, does not grow disproportionately with the problem size. The gear system doesn't blow out of control as the plasma grid gets more complex.
So the padding remains manageable, even as the problem scales.
Exactly. And that is the true prize here. While this specific 1D problem suffers from a bad condition number, higher dimensional problems behave very differently.
You mean like 3D models?
Right. When we eventually move to full 3D finite element method models, which is the math actually required to build a working stellarator or tokamak, the condition numbers scale in a way that is far more favorable to quantum algorithms.
Ah, so 1D is uniquely bad for this quantum solver, but 3D will be its playground.
You got it. By proving that high-level software can efficiently block and code the physics and keep the scaling factor stable, they have essentially paved the runway for 3D fusion models.
That is amazing.
When we drop this optimized engine into a 3D chassis, we expect to see actual polynomial speedups over classical supercomputers.
They systematically dismantled the computational roadblock. It really is a journey when you zoom out and look at the whole picture.
It really is.
We started with the massive memory bottleneck of fusion plasma. The fact that trapping the position and velocity of every particle literally chokes out classical RAM.
Right.
Then we explored the clever 1D linear workaround, focusing on the tiny perturbations to turn complex PDEs into manageable equations.
The ripples on the pond.
Exactly. From there, we looked at the massive hurdle of block encoding, using LCU to translate rigid classical beta into a reversible quantum gear system.
And the mathematical garbage.
Yes, the garbage. And finally, the massive software leap. How high-level abstraction with QMod automated the multi-control routing, slashing the required quantum resources by a factor of 100, preparing us for the 3D future of energy.
It highlights how deeply interdisciplinary this frontier is. What stands out to you? You have plasma physicists trying to contain a star, quantum hardware engineers fighting decoherence, and software compiler designers finding algebraic shortcuts to bypass the hardware limits.
Everyone is pitching in.
Yeah, they're all pushing against the exact same boundary from different angles. It makes you realize how high-level software abstraction, moving from manually wiring logic gates to using intuitive compilers, completely lowers the barrier to entry.
It lets people focus on their actual jobs.
Exactly. It allows physicists to focus entirely on the physics of the plasma rather than agonizing over how to route a single quantum gate.
It democratizes the tools needed to build the future. Which leaves me with a final thought for you to mull over.
Let's hear it.
We've seen how fragile current quantum hardware is, and how the entire industry seems to be waiting on pins and needles for the physical machines to catch up to the theory. But if software compilers like QMod can already reduce quantum resource requirements by a factor of 100 before the hardware has even fully matured, how close are we to a sudden, software-led quantum breakthrough.
A very good question.
One that makes simulating and building a working fusion reactor viable seemingly overnight. All because the code got smarter, not just the computer. Thank you for joining us for this deep dive into the quantum frontier. This was crafted just for you, and we'll catch you on the next one.